We have seen in the previous topics that discontinuities are critical for the behavior of a rock mass. Hence, for most engineering projects, it's important to detect the presence of discontinuities and characterize the discontinuities. When it comes to the field, what do we actually see of the discontinuities? Most of the time we see only a profile, as you can see on this figure here. This profile is called a trace, and that corresponds to the intersection between the discontinuity plane and a rock face. That could be a natural rock face or a cutting like on this figure. The characterization of the discontinuities is conducted by analyzing their trace, and different methods are possible for that. One option is simply to survey manually the discontinuities by sending people at the rock face, but that carries a risk of having rockfall and injuring the people involved in this operation. Another option is to drill some holes in the ground and retrieve specimens like this one. And you could see here that we can clearly identify the presence of a discontinuity on this specimen here. Another option is to actually lower a camera in the borehole and record images of the rock in the borehole and try to identify discontinuities. Finally, another option is just to go with remote operations like laser scanner or aerial photography and try to identify discontinuities through these images. The International Society for Rock Mechanics recommends characterizing 8 parameters in relation to discontinuities to fully define them. The first one is the orientation. What do we mean by orientation? If we have the plane of a discontinuity here, we need to know how inclined it is, and for a given inclination, what is its orientation. So this inclination with respect to horizontal is called the dip. And the orientation, the angle between the line of steepest gradient projected on a horizontal plane taken with respect to the north, measured clockwise, gives you what's called the dip direction. Dip and dip direction fully characterize the orientation of the discontinuity. So here we need to characterize the dip and the dip direction. I have added a graph in the additional resources defining in a graphical manner what dip and dip directions are. The second parameter we're interested in is the spacing. A rock mass typically includes many discontinuities, some of which are parallel. This is the case on this figure with the horizontal discontinuities and the vertical discontinuities. The distance between discontinuities taken perpendicular from the discontinuity plane is called spacing. This spacing can be quite variable, like for the vertical discontinuities on the figure, or fairly constant, like for the horizontal discontinuities on this figure. If there is a lot of variation in the spacing, an average value would be considered. Spacing is relevant for the behavior of the rock mass because the smaller the spacing, the higher the number of discontinuities, and hence the more the rock mass will be affected by the discontinuities. The third parameter is the continuity. Survey of discontinuities have shown that discontinuities aren't always continuous. There might be some rock bridges between joint segments that would confer extra strength to the discontinuity. This is illustrated in this photo here. The continuity is expressed as the ratio between the cumulative length of joint segments over the total length of the discontinuity. The fourth parameter is roughness. We have seen in a previous topic that roughness plays a key role in the shear strength of discontinuities. Here, roughness first has to be assessed as a large scale. The discontinuities have to be classified as planar, waved, or stepped. Then extra information is required at a small scale, and the discontinuities could be rough, smooth, or slick inside, which means polished. The fifth parameter is the wall strength. Wall strength is an important parameter because it contributes to the strength, the shear strength of the discontinuity, and has to be quantified. It's quantified usually by an indirect method called the Schmidt hammer, where a steel ball is bounced against the rock and the height of the rebound is measured, and the higher the rebound, the stronger the rock. The sixth parameter is the aperture. It is a distance between the two walls of the joint. Aperture is illustrated in this photo, and you can see that it might vary significantly for different discontinuities, again just for one discontinuity. In this case, an average value might be used. Aperture is relevant for the stability of a rock mass because typically the more open a joint, the less strength it will have. This is because aperture limits the interaction between the two walls of a discontinuity. The seventh parameter is the filling. This pertains to the material that could be found inside a discontinuity. It has to be characterized. In situ, the thickness of the filling would be measured, and then some material would be brought back to the laboratory where extra characterization would be performed. For example, the amount of moisture, the particle size, and the mineralogy of the material. The eighth parameter is the seepage. This is about providing information about the amount of water in a given site. There is information to provide at the large scale for the site and the study, but also locally into the discontinuities, how much water is flowing in the discontinuities. This seepage information consists of a rating from 1 for a very tight discontinuity where there is no obvious flow of water, so dry discontinuity, to 6, the highest value, for a discontinuity where water flows continuously. These 8 parameters are important because they help to define the potential unstable blocks in a rock mass. They help defining the number of sets of discontinuities. They help to classify the rock mass, and they also contribute to the quantification of the rock mass strength and deformability. All these aspects will be covered in later topics.